Cool. Yeah, as someone said, the talk is going to be about sums of squares. So expressing integers as sums of squares. Let me see if I can go to my iPad. I see.
Okay, just one note. Please feel free to ask any questions if you have. You can just, again, raise your hand or just, I mean, we are too few. You can just start asking your question if the speaker doesn't mind.
Yeah, please.
Right,
I might not notice if you like message or something, so you should just interrupt.
Right.
Yeah.
Okay, that's the only note.
Okay, cool. This is actually my first time doing the iPad thing, so bear with me if there's some problem. But okay, so let's get started. So the question that I want to ask and hopefully answer is, which integers n can be expressed as a sum of two squares of two perfect squares. Okay, so in other words, n, I want to write n as a squared plus b squared, where a and b are in Z. Okay, so the first thing to notice about this problem, and it's kind of a common theme in these kinds of Diophantine problems in general, is to try to factor your equation, right? So you're trying to solve, a squared plus b squared equals n. The first thing to notice is that you can write this as a plus bi times a minus bi. So then the question becomes something about factoring n, but where you're allowing yourself to use complex numbers. But since the coefficients in my complex numbers are still integers, I'm restricting myself to zi. So this factorization is taking place in zi, which is a subring of complex numbers. So just namely the complex numbers that have integer, real, and imaginary part. And these are called the Gaussian integers. And they're like one of those pretty nice number systems. They're almost as nice as Z in a lot of ways. So they have kind of a lot of the similar properties, and that's what we're going to use to try to answer this question. Okay, so just to make it a definition, the norm of a Gaussian integer is the integer that you get when you multiply it by its conjugate. So the norm of a plus bi is just the thing that we were looking at already. So a plus bi times a minus bi, which is a squared plus b squared, which is an integer. Okay. Another way to write that is if your complex number is z, it's just z times its complex conjugate, right? And so a nice fact about this norm is that it's multiplicative. So if I take the norm of z times w, right, that's the same as zw times zw bar, which I can rearrange as z bar times ww bar, which is the norm of z times the norm of w. Okay, so this norm map goes from the Gaussian integers to the integers, and it's what we call multiplicative. Okay, so one consequence of this multiplicativity is the fact that if you have a Gaussian integer and you want to know if it's invertible, then it had better be invertible when you take its norm. So units, a unit in a ring in general means an element that has a multiplicative inverse. So units in Zi are elements U such that U inverse exists, right, in Zi. So if you have a unit in Zi, its norm had better be a unit in Z by the multiplicative property. So we know that, so if U is a unit, then the norm of U has to be a unit in Z. And the only units in Z are +1 and -1. But -1 is never a norm of something because it's negative. So that means that the norm of U had better be 1. Okay? And once you have that, you can figure out what all the units are, what all the invertible elements are in Zi. So they're, complex number a plus bi with integer coefficients such that a squared plus b squared is 1. So the only things that satisfy that are ±1 and ±I. Okay. All right, so those are the units. The next fact is that this Gaussian integer number system has unique prime factorization. Okay, and so what does that mean? It means that given any Z element of Zi, I can express it as a product pi1 times pi2 times pi3 up to pi k, where each of those pi i's, such that each pi I is prime. What that means is it's not possible to factor pi I further inside the ring Zi. So I can't express it as a product of two things unless I do a stupid thing, which is I write it as one of these units times something. So that doesn't count as a factorization. So just in the same way that like 5 is the same as -1 times -5, doesn't count as a factorization in the integers. If you do like -2 is the same as I times 2i or something, that would not count as a factorization. Okay, so I'll go to a new page. Nice. Okay, so I'm not going to prove fact 2, but I'll give you kind of an idea, and it's actually not necessary for what I want to do today, but a sketch of how you would go about proving 2 if you wanted to, of proof. Is you basically need to show that you can do long division in Zi. So you can do division with remainders in Zi. So more precisely, if you have some alpha and beta in Zi, then there exists a quotient Q and a remainder R in Zi, such that alpha is equal to beta times Q plus R. And then the key property is that R has to be small compared to beta. And the way you express that is that the norm of R is less than the norm of beta. Okay, so this is very reminiscent of the statement for Z, so that the remainder is smaller than the divisor. But in this case, you want to use norms because there's no good notion of smaller than in the complex numbers. Okay, and so how do you know that you can do this? Well, it's there's a nice picture that lets you know how to do that. So remember, alpha and beta are complex numbers, so I can draw them in the complex plane. So if that's beta, then if I'm looking for Q, I should multiply beta by all possible Gaussian integers and see what kinds of things I get. So for instance, if I multiply by -I, I would get something down here. So this is -I times beta. Then the number up here would be -I times beta plus beta. So 1 -I beta. And if you continue like that, you get kind of a perpendicular lattice that consists of all the different ways of multiplying beta by a Gaussian integer. Okay, and now I was trying to divide alpha by beta. So alpha, I'm going to suppose, is some kind of random Gaussian integer. Okay, and so the process of finding Q is just the process of finding the lattice point which is closest to alpha. So in this particular example, it would be this one. So this is going to be beta times q. And that's pretty close to alpha, right? So beta times q plus r. So in this case, r would just be the arrow that points from beta q to alpha. Okay. And then the fact that the norm of r has, is smaller than the norm of beta is just the fact that because we chose beta q to be as close as possible to alpha, we know that the distance from beta q to alpha, which is r, the norm of r is going to be smaller than the size of beta. Okay. And so I don't want to go too much further. So that's how you prove that you can do division with remainder. And then it turns out that this implies unique factorization. And that's a general fact for any ring. If you have some notion of size, like a norm, and then you have some division with remainder, then you have unique prime factorization. Okay, but it's actually not true for all number systems. So for instance, so kind of beware, the number system z adjoin root minus 5. So in other words, a plus b root minus 5 does not have prime factorization. Okay, so this is not just a there are plenty of kind of number systems that are lying around that don't have this. Okay, but that was a little bit of an aside because we don't, like I said, we don't actually need to know the full strength of that for what I want to do. So what is it that I want to do? So my original goal was to try to figure out which numbers you can write as a sum of two squares. Right, so I started with my number n, and I want to write it as a sum of two squares. So the first thing I want to do is factor it in z. So n is going to be p1 times p2 up to pm. So this is just a factorization in z. Okay, and the next observation is that if I can answer my question for each of those prime numbers, then I can answer the question for n as well. So if I could write p1 as a1 squared plus b1 squared, and I could write p2 as a2 squared plus b2 squared, and so on and so forth for all these primes, then I'd be in good shape, because that would mean that p is equal to some z1 times z1 bar. This one is z2 times z2 bar. This one is zm times zm bar, right? So that would mean that I was able to write my n as z1 z1 bar times z2 z2 bar times all the way up to zm zm bar. And then if I just group those together, z1 z2 up to zm times z1 z2 up to zm all bar, then I've written my n as some Gaussian integer times its conjugate, right? So then I've if this entire thing is, say, capital A plus capital BI or something like that, then this entire thing is going to be its conjugate, so capital A minus capital BI. So then I will have written my number n as a squared plus b squared. Okay, so that little observation all rests upon this big if, right? So if I can solve a problem for each of those prime factors, then I can solve it for n, right? So now I want to just look at a slightly simpler problem, which is just to try to write prime numbers as a sum of two squares. Okay, so next page. All right, so let's just kind of do some experiments. So if we look at the first few primes, so the silly one is 2. If you think for a second, you can write that one as a sum of two squares, right? It's 1 squared plus 1 squared. How about 3? 3. Seems like you can't. Okay, next prime up is 5. Is 1 squared plus 2 squared. 7. You can think for a minute, but I don't think you can. 11, same issue. 13, we're back to being in good shape. So it's 9 plus 4. Okay. So as you can see, unfortunately, not all primes can be written as sum of two squares. Does anybody know what the rule is that distinguishes the primes from the good ones from the bad ones?
Should I say it?
Yeah.
You have to look mod 4.
Yeah. So this is the kind of thing, if you're like Fermat or one of these early people, you probably calculated like a couple hundred of them, and you looked for the pattern, and you noticed that, so 2 is kind of a special case, but besides 2, every odd prime is either 1 or 3 mod 4. Right? And so 3 is obviously 3 mod 4. 5 is 1 mod 4. 7 is 3 mod 4. 11 is 3 mod 4. 13 is 1 mod 4. Right? When I say mod 4, I mean the remainder that's left over when you divide by 4. Okay. So, and that turns out to be a theorem. Okay, so that's what's called the Fermat 2 squares theorem. It's a bit easier than some of his other theorems. But what it says is that if, so a prime P can be written as a squared plus b squared if and only if P is congruent to 1 mod 4 or 2, right? But that 2 is only to take care of the case of the prime 2, so it's not so important. All right. So in other words, so if you're 3 mod 4, it's not possible, and if you're 1 mod 4, it is. Okay, so this is the theorem that I want to prove. Okay. So the first thing to notice is that if you look at perfect squares mod 4, so look at perfect squares mod 4. So 0 squared is 0 mod 4. 1 squared is 1. 2 squared is 0. And 3 squared is 1 mod 4. Okay, and that's all I need to do, because if I go to higher numbers, it's just going to repeat. Okay, so any perfect square is either 0 or 1 mod 4. So if I add 2 of them together, what can I get? So a squared plus b squared, if I look mod 4, it could be 0, right? Because you could do 0 plus 0, or it could be 1, or it could be 2, right? But it couldn't possibly be 3, right? So there's no way to add 2 of those numbers and get 3. So this implies that it's impossible to write a prime which is 3 mod 4 as a squared plus b squared. Okay, so that's one direction kind of this theorem, and that's what's called the trivial direction. Because if you're familiar with kind of modular arithmetic and how that works, then it just comes down to checking, to doing this check that I just wrote down. Okay. So the point is that, yeah, when you write a sum of 2 squares, the answer is always either 0, 1, or 2 mod 4. So you can't possibly get a prime that's 3 mod 4. All right, so if that's okay, we're going to move on to the interesting part, or the more tricky part of the proof, which is an existence theorem. So I claim, so the next part is claim if my prime is congruent to 1 mod 4, then we can write it as a sum of 2 squares. Okay, and there's a lot of different proofs of this, and Fermat came up with a good one. I think Gauss and Legendre also came up with good ones. But what I want to tell you today is a kind of recent proof that was proved by Don Zagier. So This is due to Zagier. I don't know exactly when, but he's still alive, so it's not that old. And it's pretty clever, as a lot of his stuff is. So I think it's it's kind of my favorite one that I've seen because it's really simple and it's pretty short, and you don't need to. There's just very few ingredients. Okay. So here's the idea. So we have this fix your prime that's 1 mod 4, and I want to try to solve this Diophantine equation, right? So I want to solve. So we want to solve P is equal to A squared plus B squared. Now, because P is an odd prime, one of A or B has to be odd, and the other one has to be even, right? Adding up two things to get an odd thing, there has to be one of each. So I'm going to rename. I'm going to assume that B is that even one. So let's rename B to be 2 times something. Okay, so from now on, we're going to rename B to be 2 times something else. Maybe if you want, we can say 2 times B prime. Okay, so I'm trying to solve the equation P is equal to A squared plus 4B prime squared. Right? Okay. And so the key trick that Zagier came up with is to relax a little and try to solve a much simpler equation. So try to solve the equation P is equal to A squared plus 4 times B times C. Okay. And I'm only trying to solve these in the natural numbers. So I'm looking for solutions in n. So I guess in n cubed now, because there's 3 unknowns, right? P we already fixed. We fixed that at the beginning of the page. So I'm trying to find A, B, and C, which solve this. Okay. So the first observation is that the set of all A, B, and C solving this Diophantine equation is non-empty. So that there are, so first notice, there are solutions. It's not too hard to find one. So because P is equal to 1 mod 4, I know, for instance, that P is equal to like 4k plus 1 for some number k, right? So I could do P is equal to 1 squared plus 4 times k times 1, right? So in other words, A is equal to 1, B is equal to k, and C is equal to 1 would be a solution, right? Now that's not very useful because we were originally trying to solve this one, right? We really wanted, this was our goal, was to solve this one. And that would mean that B and C would have to be equal, right? So the fact that B and C are k and 1 doesn't really help us, okay? But it will actually still get us there in the end. So the next thing to realize is that, so the next observation is that there's an involution on the set of solutions. So there is an involution on the solution set, the set of all A, B, and C which solve this. And it's kind of silly, you just swap B and C, right? So B swapping with C. If I have a solution A, B, and C, then A, C, and B will also be a solution, right? That's just because when you multiply 2 numbers together in an opposite order, it's the same thing, right? So that's kind of clear. And we are looking for solutions which are fixed by this involution, right? Because if you have a solution which, when I switch B and C, it's actually the same solution, that means that B and C are equal, right? And that's what I originally wanted. Okay, so that's the next thing. So far, none of the things I said are particularly insightful. They're kind of obvious. But now here comes the kind of the clever thing. So the third thing to realize is that there is another involution on the set of solutions. Okay, and this is what Zagier came up with. So suppose you have a solution A, B, and C. So given your A, B, and your C, such that P is equal to A squared plus 4BC, I can write this, I can draw a picture of the solution as a windmill. Okay, so first I'm going to make I'm going to arrange P blocks into a windmill configuration. So first I'm going to have A squared blocks arranged in a square.
Excuse me. I just want to say, like, if anyone doesn't know, an involution means a map that squares to the identity. So it's its own inverse.
Yeah, thanks. Yeah, so yeah, as you say, involution is just something that you can do such that if you do it again, you get back to where you started. So swapping two things is a good example of that. And then the thing I'm about to do is a little bit more complicated, but it also has that feature. Okay, so the construction is that I have my solution in hand. So P is equal to A squared plus 4BC. So what that means is I can make a little arrangement of blocks where I arrange A squared blocks into a square. And then I'm going to make a rectangle of area BC and make 4 copies of it, and then arrange them so line up one edge of that rectangle with the edge of the square, and then do the same thing with the other 4 copies of it. Okay, so let's say maybe B, this is B and this is C or something like that. All right. Now, there's 2 ways that I could have done that, right? So I could have done BC like that, or I could have done BC the other way. So another way I could have done it is, this is my A squared. I could have lined it up so that the long one was going outward like that. Okay, so this is the old involution. This is the involution where I just reversed my B and my C. So this is the old involution in terms of pictures. Now the new involution is to draw the same shape, but broken down in a different way. So instead, I'm going to kind of make a larger square. So you can kind of imagine filling in a much larger square like that. And then what's left over is just these little nubs coming off like that. Okay, so the point is that this is now a very different solution, right? So this is a new A. So this, I'll call it maybe A tilde squared, right? And then this is maybe B tilde, and this is C tilde. Okay, so by kind of redistributing where I want the interior square to be and where I want the outside rectangles to be, I can get the exact same shape. So if I colored all this stuff in, they would look exactly the same. So it's the same total number of blocks. So this is still P blocks total, but decomposed in a very different way. And so the way you can remember how to go back and forth is that one of them has overhanging rectangles, and the other one doesn't. So this is no overhang. All right. I wanted to describe. And what it does is it takes a picture where you have overhanging rectangles and replaces it with a picture that has no overhang, and vice versa. If you have no overhang, there's a way to redraw that picture in such a way that you have overhang. So just to do one more example, suppose you had some picture like this. Right, so this is no overhang. How would you draw the new one? So this is the new involution. So an involution is just a way to, given one solution, to come up with a new one. Right? So what you do is you start cutting along here. Okay, and then this now becomes, so the new picture then has a much smaller core square, and then has much larger windmill rectangles coming off of it. Anyways, so you kind of get the point. So these are the same, right? The same total number of blocks. But just broken down in a different way, right? So I think this takes a minute to kind of to wrap your head around, but you can convince yourself that actually for any solution, if you draw this windmill and then cut it up in a slightly different way, you can get a new solution from that. And it's a very non-obvious way of producing new solutions. Okay. One thing to think about is that what if when you started when you started arranging your solutions as a windmill like this, what if you had this kind of situation where they kind of locked up nicely into a big square, right? How am I supposed to get a new thing from that? And the answer is this never happens, right? Because this has a total of m squared blocks. And that would mean that m squared is equal to p. But p is a prime number, so that can't happen. Okay, so you'll never close up to be a larger square when you do this, because p is prime. Okay, and then another issue is that, well, what if you like this, where the length of b matches up exactly with the length of a. Right, so you have one of these kinds of things. How are you going to come up with a new solution based on that? And the answer is that you can't. And these are the fixed points. So this is a fixed by the involution, by the new involution. Okay. But if that's the case, then what this means is that a, so the side length of a is the same as the side length of b, right? So in other words, you've written p as a squared plus 4ac. In other words, a times a plus 4c. Now, again, because p is prime, the only way for this to happen is for a to be 1. So the only way this is possible is when a is equal to 1. Again, because p is prime. Okay, so maybe this is not really a super accurate picture. So really, this doesn't really happen. What really happens is you have like a tiny block in the middle, and then you have very long spokes coming out. Okay. And so this one is the unique solution that is fixed under the new Zagier involution. Okay, so fine. Honestly, like you probably need to kind of think about it a little bit to get used to how you go back and forth for these. But if you just kind of accept for a minute what I'm saying, which is that there's a way of producing a new solution from an old solution in such a way that the only way that it doesn't change it is if you have this particular plus sign. Then a consequence of that is that the total number of solutions is odd. So the number of solutions A, B, C is an odd number, right? Because you can, right, every time you have a solution, you have a partner, except there's one particular one which is left alone, right? So that's the kind of the odd one out. So the total number of solutions is odd, right? Now go back to our stupid involution of just switching B and C, right? That's also an involution. And when you have an odd number of things and you have an involution, that means that every single thing has a partner except for one, right? So there's going to be an odd one out for that other involution as well. Here's how the logic goes. So using the new involution, the solution set is odd. And that implies that the old involution, which was just swapping B and C, has a fixed point. In other words, there is some solution which doesn't change when I swap B and C, right? In other words, you can find a solution such that B and C are equal, right? So it's P squared is equal to A squared plus 4B squared, right? And that's what we wanted. Right, so B is equal to C. And as it turns out, we'll see later that actually that's also unique. So each of those involutions has a unique fixed point. And yeah, for the stupid involution, the old involution, the fixed point is actually the thing that we were after. And for the new involution, the fixed point was this big plus sign. So you really need both of them kind of playing together to deduce the answer that you want. Okay, and so that completes the proof of Fermat. So now we can go back, we can finally answer the original question, which was, now we actually know how to say which numbers you can write as a sum of two squares. So given a number n, I want to decide that, again, I take its prime factorization first. So n is p1 times p2 times p3 times pk. And some of these primes are going to be 1 mod 4, and some of them are going to be 3 mod 4. So maybe let's name them differently. So the p's are going to be the ones which are 1 mod 4. And let's call the q's the ones which are, so q1 up through ql are the ones which are 3 mod 4. All right, so if we name them in that way, then you can write your p's as pi1 times pi1 bar, pi2 times pi2 bar, pi3 times pi3 bar, right? That's just the fact that you can write each of those primes as a sum of two squares. Okay, and then the q's, unfortunately, you can't, right? So the q's just have to stay alone. So the q1, q2, up to ql. Okay, and so how are we gonna, at the end of the day, I want to write my n as, oops, let's see if I can go back. It's a bit embarrassing. All right, well, I'll just write it again. So n, if you start with your n, which is p1 up through pk times q1 up through ql, and these ones are the ones which are 1 mod 4, and these are the ones which are 3 mod 4. Then each of the ones which are 1 mod 4, you can write as some complex, some Gaussian integer times its conjugate, pk times pk bar, and the other ones just get left as is, right? q2 to ql. And so our original goal was to write n as a sum of two squares. So I wanted to write it as some Gaussian integer z times z bar, right? So how am I going to possibly do this? So this is the big question. So my only chance of doing this is going to be to group all pi1, pi2 up to pik together, and then pi1 bar, pi2 bar to pik bar together. And then I want to distribute these q's. So the q's are actually primes. So these are prime in zi. right? Because you can't factor that. If you could factor Q and Zi, then that would give you a factorization of, right? It would be writing them as a sum of two squares, right? So the norm of Q1 is just Q1 squared. And if you could somehow factor Q in Zi, taking the norm of each of those guys would give you a sum of two squares for those. So the fact that you can't write them as a sum of two squares means that these Qs are actually prime as elements of the Gaussian integers. So you really can't split those up any further. So all you can really do is distribute them on either side. So if you're lucky, you can put like a Q1 here and also a Q1 here, and a Q2 here and also a Q2 here, right? And since these are integers, you know, when you take their conjugates, they don't change. So the answer to the question in the end is n is expressible as a squared plus b squared if and only if the primes qi, which are 3 mod 4, these are sort of the offensive ones, appear an even number of times each. Each appear an even number of times. Okay, does that make sense? So in other words, so for instance, if you have, you know, if you took your number, which let's see, just as an example, suppose that your number was 18, right? 18, if you take its prime factorization, you get 2 times 3 times 3, right? You can write, so 2 is one of those good ones. You can write it as 1 plus I times 1 minus I. But 3 is not. So the only chance you have of getting your 18 as a sum of two squares is just to distribute those 3's. One of them is going to go with the 1 plus I times 3. And then the other one is going to go with the 1 minus I. Sorry. Right. And so then at the end of the day, you have 3 plus 3i times 3 minus 3i. Right. Which is 3 squared plus 3 squared. Okay. Just to kind of get a sense of how that works. And if you had, so what's another one that's bad? So if you had like a 7 over here, so what's 18 times 7? 126. So if you had 2 times 3 times 3 times 7, then you're in bad shape. So this is impossible, right? Because so the 2 is okay. The 2 is great. The fact that there's 2 3s is also good because you can split them evenly. You can put 1 3 with one of the, and then the other one with the conjugate. But the fact that there's only a single 7, and 7 is 3 mod 4, and it only appears once. And 1 is odd. Means that it's not possible. Okay, so now hopefully, if you kind of followed all those steps, you now know how to decide which numbers you can write as a sum of two squares. Okay. By the way, how much time is left before we're done?
I think about 10 minutes or so.
Okay. Cool. So that's the 2 squares question. The 3 squares question, so that was answered by Fermat. Legendre was able to say which n which ends are writable as a sum of 3 squares, a squared plus b squared plus c squared. Okay, and the answer is a bit weird, and I don't even remember what it is. You can look it up, but the proof is also pretty hard. So the answer is like some can, a lot can't, and they're kind of all over the place. And then the next question was answered by Lagrange, who's actually a different person. And he proved that every number n is expressible as a sum of 4 squares. So a squared plus b squared plus c squared plus d squared. Okay, and I think so that's kind of the main interesting one. Unfortunately, I don't know of any proof of that is as slick as the Zagier one, where you just kind of arrange the blocks. All the proofs I know really use some number theory, so it's kind of a way to get around that. But I will give a hint for kind of how you go about that. So the idea, so the theorem by Lagrange is that any n can be expressed as a squared plus b squared plus c squared plus d squared. So the trick is to use a number system which is kind of like the Gaussian integers, but which lives inside the quaternions. So these are called the Hurwitz integers. So the idea is to use the Hurwitz integers, which are numbers of the form a plus bi plus cj plus dk, where these are the quaternions. So I'm not going to, maybe I won't define what the quaternions are. The quaternions are like this number system which is associative but not commutative, and it has the feature that I squared is -1, j squared is -1, k squared is -1, and then ij equals k, jk equals I. And I think that might be it. Okay, so this is some new number system that's slightly more advanced than the complex numbers, and you can again look at those which have integer coefficients. So the Hurwitz integers are those for which a, b, c, and d are integers, or a, b, c, and d are all half integer. Okay, so that's some number system, and you have a norm again. So you still have the norm of some Hurwitz integer alpha is defined to be alpha times alpha bar. This is the definition. Where alpha bar, so if this one is alpha, then alpha bar is just a minus bi minus cj minus dk. Okay, so you just take the conjugate on all the different imaginary parts. And by a similar proof as before, you can show that it's multiplicative. So n is a function from the Hurwitz integers, which are called h, to the usual integers, and it's multiplicative. Okay, and so if you have a prime number in Z, if one of your prime numbers in Z is factorizable in H, so it factors into alpha times beta in this Hurwitz number system, then if you take the norm of both sides, you get n of p is equal to n of alpha times n of beta. And now, what's n of p? Well, n of p is so the sum of squares, but p is just a regular integer, so it only has a, right? So n of p is just p squared, right? Is equal to n of alpha times n of beta. Okay. And then because P is prime in Z, so now these are all integers, right? So these are integers. As long as alpha, neither alpha nor beta was a unit. So as long as this is a true factorization, then you get that that P is equal to n of alpha. In other words, P is a sum of 4 squares. Okay. So I don't have time to explain why, but it's a fact that any integer prime can be factored in the Hurwitz integers. And the Hurwitz integers are kind of crazy because they don't have unique factorization. So you can kind of factor things left and right. And the fact that you have so much factoring flexibility basically implies that you can write any number as a sum of 4 squares. Okay. So the last thing I want to say is how many ways can you? So if every number can be writable as a sum of 4 squares, the natural follow-up question is in how many ways? So in how many ways can you write n as a sum of 4 squares? Okay, and to answer that question, you use what's called a generating function, which is a trick from combinatorics. So you consider the following power series. The sum from n equals minus infinity to infinity of q to the m squared. Okay, where q is just a variable, right? It's a power series. So and then if we raise this to the 4th power, the answer will be the sum from n equals 0 to infinity of R4 of n times q to the n, where R4 of n is the number of ways to write n as a sum of 4 squares. Okay, so this fact is completely obvious if you write down. So what happens when you try to expand out this infinite? So it's a product of 4 infinite series. If you kind of combine the terms, you find out that each factor of q to the n, or each term of q to the n that appears, has to be obtained by multiplying together a term from each of these 4 things, right? And when you multiply it, q to the n squared times q to the m squared, it's q to the n squared plus m squared. So the point is that, so q to the n1 squared times q to the n2 squared times q to the n3 squared times q to the n4 squared is q to the n1 squared plus n2 squared plus n3 squared plus n4 squared. All right, so this is not like a new idea. This is just kind of a reshuffling of the same problem, okay, which kind of phrased it in a different way. But then the surprising fact is that this function, f of q, is a very special function called a modular form. So the surprising fact, which was realized by Ramanujan, is that this f of q is a modular form. And as soon as you know something is a modular form, you're in business. Because so modular forms are special. Basically, I don't want to get into it too much, but a modular form is a holomorphic function from the upper half plane to the complex numbers, which has a few special properties. And the main property is that it's periodic. So f can be written as a Fourier expansion in Q. So if tau is the variable in the upper half plane, then Q is e to the 2 pi I tau. So it's sum of from n equals 0 to infinity of a n q to the n. And anytime you have a modular form, it has 2 features. It has a weight, k, and it has a level, m. And once you fix the weight and the level, the set of all possible modular forms of that weight and level is finite dimensional. What that means is that if you know the first few coefficients that determines the entire power series. And we have a list of what all the modular forms are, or at least a basis for the space of modular forms of every weight and level. So as soon as you know that a function is a modular form, you can just calculate what are its first couple coefficients, and then you know the entire power series. And this is basically the main insight of Ramanujan and kind of what he contributed to math. So I would say this was one of the first big triumphs of that realization. And unfortunately, I guess I'm out of time, so I'm not going to say any more about modular forms, but maybe this is a good preview for learning more about them.
Okay, thank you very much. I don't know if it's possible to clap. I don't know. But yeah, thank you. So if anyone has any questions, please just unmute yourself and ask your questions. Okay, so I think, yeah, I don't see anyone unmuted. Ajmin, do you have a question?
Oh, yeah. So like, so can you hear me?
Yeah.
Oh, so like this f of q, it's this sum from negative infinity to infinity. Why do you go from negative infinity instead of from 0?
Yeah, that's a good point. It doesn't really matter. So you could go from 0, but if you go from 0, it's not a modular form. So basically what the point is that if you go from negative infinity to infinity, you're allowing like negative 3 squared plus 2 squared to count as well as positive 3 squared plus 2 squared, right? So when you do sums of squares, if you allow negative numbers to be squared, it doesn't really matter because of course you can always just do it with positive numbers. But yeah, I wrote it because to be actually correct, f of q is a modular form only if you use the full one. And by the way, I mean, what is this, right? This series is just 1 plus 2q plus 2q to the 4th plus 2q to the 9th. Sorry, not f of q. That's just the infinite sum in there, right? Plus 2q to the 16th plus 2q to the 25th. Okay, so the point is that if you only sum from n equals 0 to infinity, all those 2's would be 1's. So it's really not a big difference. But this property of being a modular form is very delicate because it uses a very different side of math. So if you make just a kind of a silly tweak on the combinatoric side, it breaks the modularity property on the other side. So the answer is this kind of technical reasons, but I wanted to write the correct formula there.
Okay, any other questions? Okay, thank you very much, François.
Okay.
Thank you for
Thank you,
coming and starting our first meeting after the break.